So, in the last few classes, we discussed why there should be a third particle in beta decay, a very light neutral particle, and later on we looked at the efforts that were made to actually detect it. Even as this whole story was going on, already some problems have started. Problem is with this particle called muon. One can actually have 2 or 3 or maybe more lectures about the discovery of muon itself, but I will spend a few minutes on muon, partly because Homi Bhabha had a lot to do with it. Scientifically, he's known for two things. One is, of course, Bhabha scattering, that is scattering of electron and positron. And second is less well known, but where he actually spent a lot of time. And in fact, I have seen an article written by a cosmic ray physicist who actually argued that Bhabha deserved a Nobel Prize for his work on muon. So people have been studying cosmic rays, I don't know, from around 1900 or so, and they have established various properties of cosmic rays. In fact, I believe there was some doubt whether these particles are coming from above or from below, from Earth. And this problem was solved by putting a detector in a sea and taking it deeper and deeper and show that the activity becomes less and less. So it's the proof that they are coming from above rather than below. And the study of cosmic rays, originally they were studied at high altitudes, but later people started looking and found that there is cosmic ray activity at low altitudes also, in fact even at sea level. And by that time people identified electron, proton, neutron, and of course all the various nuclei. Proton, neutron, and all the nuclei, they have strong interactions, which is much stronger than electromagnetic interaction. So if you have a high energy particle coming from outer space and enters the atmosphere, it cannot have very long mean free path. It will interact with something or other very soon. If you have an electron, high energy electron, again once it enters atmosphere, it will pass in the neighborhood of a nucleus, and the Coulomb force makes it emit a high energy photon, which will pair produce into electron positron pairs. So this 1 GeV electron will soon lose its energy very fast. But at sea level, you see particles with energy 1 GeV. They can't be strongly interacting particles. They can't be electrons. But they are electrically charged because they are leaving signals in your detectors. So people first named it, I believe it is Bhabha who named it the penetrating component of cosmic rays, and established that this is something, the properties of this penetrating component cannot be explained if it is a atomic nucleus or a neutron or an electron. And around 38 or so, various people actually identified it to be a charged particle with the unit charge and mass about 200 times more massive than electron. And people got very excited, especially because just a couple of years before, Yukawa proposed that the binding within a nucleus is due to the exchange of a particle with a mass of about 100 MeV. But very soon it was found that this particle does not have strong interactions, which is why it is the penetrating component. So this is not the Yukawa particle, and it's just a coincidence that its mass is close to the mass predicted by Yukawa. And Bhabha's name is attached to another aspect of muon. So the studies of muon established that it has a lifetime of about 2 microseconds. So if you calculate C tau, then this is 3 into 10 power 8 into 2 into 10 power minus 6. That is so the maximum distance a muon can travel is about half a kilometer. But we know that the thickness of atmosphere is about 10 to 20 kilometers. And even if you assume that the muon is produced at the top of the atmosphere, it is traveling 10 kilometers and you observe it at sea level. So how can something with a lifetime of 2 microseconds, how can it travel 10 kilometers? And this is where Bhabha pointed out of the relativistic time dilation. So in the rest frame of muon, its lifetime is 2 microseconds. But in our frame, it is moving with energy of about 1 GeV. So with the corresponding speed, and the corresponding gamma is about 10 energy by mass. So in the frame of Earth, the lifetime we measure is gamma C tau rather than C tau. Therefore, you get a factor of 10 boost, and that is how you are able to see the muons at sea level. Anyway, all of this has nothing to do with neutrinos. I just wanted to give this background because all this work is connected with the name of Homi Bhabha. The neutrinos come in when we look at the decays of so when you observe this muon, you find that The negative muon decays into electron and nothing. And similarly, positive muon decays into mu plus and nothing. Obviously, this nothing cannot be nothing, because otherwise you have violation of energy conservation. Question is nothing one or two or more? If it is just one particle, what can you say about the electron energy? It is fixed in terms of muon mass and electron mass. But when you measure the energy of electron, you find the familiar Curie plot. So we apply the same logic we had in the case of beta decay and say that muon decay is in E minus plus mu1 plus mu2. There are two neutrinos which are being produced in muon decay. It's a 3-body decay. If it is 4 or 5-body decay, I will not have this shape. I have some other shape. So this shape I get only with 3-body decays. This now gives rise to another question. Is mu1 same as mu2, or is I'll write it there. Is mu2 the antiparticle of mu1, or mu2 has nothing whatsoever to do with mu1? And people made an argument ruling out because this is a slightly involved argument. I will give a somewhat hand-waving explanation. So first, let us consider this decay, muon decaying into an electron and a photon. Is it allowed by all the known conservation laws? Energy conservation, it's possible. Momentum conservation, okay, muon is at rest, electron and photon come back to back. Electric charge conservation, possible. And angular momentum, this is spin half, this is spin half, this is spin 1. And if I combine spin half and spin 1, I can get spin half. So by all the known sacred conservation laws, this decay should occur. I mean, is allowed by all the known conservation laws. And this is actually a fundamental unwritten rule in quantum theory, whether you are doing quantum mechanics, relativistic quantum mechanics, quantum field theory. If anything is not explicitly forbidden, it must occur. Whereas this is not forbidden, yet So far, we have not seen any evidence for this. And people argue that the fact that we do not see it at certain level would imply that these two neutrinos in muon decay cannot be antiparticles of each other. The argument, this is a hand waving argument if you wish. So let's draw a Feynman diagram for muon decay. And I draw it as a 4 Fermi. And if these are particle-antiparticle, then this is mu1 and this is mu1 bar. Antiparticle I put the opposite way. In which case I can close this loop. And of course, neutrino is neutral, so it doesn't couple to a photon. But, and this is where one has to go into the details of the argument to fully understand. But what we can argue is that mu1 bar can go into vacuum, and vacuum can give rise to a photon. There is a non-zero amplitude for mu1 bar to go into vacuum, and there is a non-zero amplitude for vacuum to give rise to a photon. That's exactly how we explain the de-excitation of an atom. How does the electron go from 2p state to 1s state while emitting a photon? We say that the electron is interacting with the background electromagnetic field in the vacuum, and that is what is giving rise to this photon. So, but this mu1 bar being neutral actually are not interacting with the background electromagnetic field. But I can then put other possible intermediate states, make them interact, and eventually give rise to a photon. So this amplitude in general is non-zero, and this amplitude is non-zero. So in general there is a non-zero amplitude for it to happen, but we don't see it happening, which means that we should rule out this possibility that the two neutrinos that are being emitted in muon decay, they cannot be particle-antiparticle of each other.
Sir,
yeah.
Is it not possible that the neutrino and anti-neutrino goes in different directions so that they do not interact?
No, that is what is happening actually in the lab. But as I said, there is a non-zero probability for them to undergo this annihilation also.
I mean, the probability may be so much low that we cannot detect.
Yeah, but as I said, somebody developed a theory, and based on that theory, they predicted that the branching ratio should be about 10 to the minus 5, 10 to the minus 6. Based on this kind of argument. Let me emphasize, what I am giving here is a hand waving argument. More exact argument requires more details. I'm not doing all that. So basically we need the concept of Okay, I'll spend a little time talking about it because this we discussed little before. So 4 Fermi interaction we write as a point interaction, all 4 fermions interacting at a point. But we discussed this before that in principle we can split it and put a exchange particle. So where neutron is going to proton and the electron and neutrino are at the other vertex. So let us draw a similar diagram for mu minus and let's say mu 2 or mu 1. Now I connect, if nu 1 and nu 2 are particle antiparticle, I connect these two. Now where do I put the photon? I cannot put the photon here, but this is a charged particle. It can connect to a photon. So I can put a photon here. And all I need to know is the mass of this particle and it has unit charge. So mass of this particle I sort of estimate based on comparing this diagram to the Fermi coupling constant, and I can calculate the rate for mu to E gamma coming from this diagram. And the prediction comes out to be branching ratio is about 10 to the minus 5 or 10 to the minus 6. And within a few years, people established that the branching ratio is smaller than 10 to the minus 6. So that's why we rule this out. The possibility that the two neutrinos which are emitted are antiparticles of each other, that we rule out. So in that sense, there are two possibilities. Now nu 1 and nu 2 are same, or nu 1 and nu 2 have nothing whatsoever to do with each other. And if you remember, we introduced the concept of lepton number, where we originally said L is +1 for electron and neutrino, -1 for positron and anti-neutrino, 0 for and we say L should be conserved in all interactions. But if I say that muon decay also should be, how do I explain muon decay? So already I get a hint that I have to expand this concept of lepton number. So what people eventually did is to introduce two lepton numbers. The first one was called Le because it is non-zero only for electron and its corresponding neutrino, which is called mu E, and it is -1 for antiparticle of electron and the antiparticle of this neutrino, which is called nu e bar, and 0 for everything else. And similarly, it was defined L mu plus 1 for mu minus and a neutrino which couples only to muon, which we call mu minus 1 for mu plus and the corresponding anti-neutrino, and 0 for everything else. And we declare that both Le and L mu are conserved individual. That is, Le is conserved and L mu is conserved, not Le plus L mu. If we make that assumption, then beta decay fine, no problem. Muon decay, mu minus decay is E minus. There is Le plus 1 here, so Le minus 1 has to be there. So mu E bar and mu. And similarly, mu plus would be E plus mu E mu bar. And you see that why E to mu gamma is not allowed, because it is violating both E, Le and L mu. And similarly, you also do not see this decay also is allowed by energy momentum conservation, angular momentum conservation and charge conservation, but the conservation of Le and L mu does not allow this decay. So this is called second neutrino hypothesis, that there are two distinct neutrinos. One couples to electron and its anti-neutrino couples to positron, and the second neutrino couples to mu minus and its anti-neutrino couples to mu plus. And if you insist that there are two separate neutrinos, each with its own individual lepton number, then all the known decays can be observed. Fine, I mean, it's a nice hypothesis, just like Pauli's hypothesis is a nice hypothesis. But is it true? So, to test it, an experiment was set up, which is called second neutrino experiment. And now the conditions that the experimenters had to satisfy here are more difficult compared to Cohen-Reines experiment. In Cohen-Reines experiment, there are two main difficulties, lot of other difficulties. The two main difficulties, number one, we need a source of large number of antineutrinos. Okay, having a nuclear reactor solved that. And second, how to uniquely identify the signal. So identifying the positron and neutron both solved that. Here again, once again, we need a source of large number of neutrinos. So at Brookhaven, they developed a new accelerator in late 50s, early 60s. So that accelerator could provide a large number of neutrinos. That is point number one. Point number two is they want to test whether there is a second neutrino, and according to this hypothesis, the second neutrino couples only to muons. So if it interacts with the matter, it should produce a muon. Producing muon requires minimum 110 MeV energy, which means your neutrino should have a large energy. That is why the accelerator comes into play here. You can't do this experiment with a reactor neutrinos. Of course, in the reactor there are no muons, so that's another issue. But how did they produce these neutrinos? And here nature provided a huge boost to this experiment. The particle that was conjectured by Yukawa, which we now call pion, it was discovered in cosmic rays in late 40s. And here again, I believe there is an Indian connection, though sort of tangential. Between 1939 to 1945, whole of Europe was busy murdering each other. India was relatively untouched. So there's a physicist at Calcutta called D.M. Bose who developed a photographic technique by which he could capture fast processes occurring in cosmic rays. And it seems in sometime in 41 or so, he took his equipment to Himalayas and studied cosmic rays there. And the story is apparently he has seen some tantalizing signals. Unfortunately, he could not get better photographic plates, so that his experiment sort of got stuck there. And after the war, people with access to better photographic techniques, they could identify the pion whose lifetime was 100 times smaller than the lifetime of muon, but whose mass is only 140 MeV, just a little more massive than muon. And when you study the decay of pion, you see that it decays into a mu plus and nothing. So same question as before. Does this nothing consist of one particle, two particles, more particles?
Pion also decays by a weak interaction.
Yeah.
Muon also decays by a weak interaction.
Yeah.
Why is the difference like?
It's because of lot of technical details. I mean, what the question you asked actually is a very valid question, because according to Fermi's golden rule, decay rate depends on two things. Number one, the coupling constant. Number two, the phase space. And if both are decaying due to weak interaction, coupling constant is the same. And masses are roughly the same, so phase space is not very different. Though, mind you, as it turns out, this is a 2-body phase space, that is a 3-body phase space, but okay, phase space maybe can give you a difference of factor of 10. So why is there a difference? The difference is occurring because the dynamics of there are some issues related to the dynamics which are different in the case of muon and pion, which is why the lifetimes differ by a factor of 10 and not 10, 100. And so we study this nothing by studying the energy of the muon, and there we find that the energy of muon is fixed. So this nothing consists of just one particle. And now we apply our hard-earned knowledge about the lepton number. So this is mu will now this is what the Brookhaven people did. The accelerator accelerates protons. So you have a intense beam of protons goes and hits a nuclear target, and that interaction of high energy protons with nuclei will produce lot of pions, both pi pluses and pi minuses, and you selectively choose you have an electromagnetic separator, so you choose pi pluses and you focus them and let them decay. Pi pluses decay into mu plus and nu mu. Nu mu will eventually decay, mu plus will eventually decay and nu mu will go straight through. So schematically the arrangement looks like this. This is the target, you have the proton beam coming, and you have these pi pluses and pi minuses, and you have this so-called focusing, and then you have a decay pipe, and from this decay pipe you have both mu plus and nu mu coming out, and you have 100 meters of mud, and then here you build your detector. This is the basic schematic of the experiment. So this electromagnetic separator throws out pi minuses, collects pi pluses and focuses them into a beam, and in the decay pipe the pi plus decays, giving mu plus and nu mu in the form of a beam, and the mu plus within this 100 meters of mud, it is stopped and it decays, and its decay products will go in. It's decaying at rest, so its decay products will go in all directions. Whereas the nu mu, which is focused, will go enter the detector, and hopefully some of them will interact and produce a final signal. And in order to, and what was the signal they were looking for? So this mu will interact with a neutron in the detector, produce a mu minus and a proton. Note that again I am conserving L mu 1 on left hand side and L mu 1 on right hand side. And they have designed the experiment so that the new mu will have an average energy of about 1 to 2 energy more than 1 GeV, so that it is well above the threshold and you have a high energy muon which is easy to identify. Whereas if nu1 is same as nu2, then there is a single neutrino which is coupling both to electrons and muons. So in that case you will have this single neutrino interacting. Sometimes it produces a muon and sometimes it produces an electron. If it's a single neutrino which is capable of coupling both to electron and muon. Mind you, if there is a single neutrino, then the concept of Le and L mu goes out of window. But we have to consider all possible hypotheses. So what the experimenters look for are, they look for events of this type and this type both. And I believe the INO students, you are doing a experimental lab dealing with muons, and a high energy muon leaves a very clean signature in your detector, whereas a high energy electron, it showers and the signature looks quite fuzzy. So that was the distinction they looked for, and they saw only muon events and no recognizable electron events. They actually saw some fuzzy events, but they said we can't say it's electron, and later people believed that those fuzzy events are due to what are now called neutral currents, but that's a separate story. But the conclusion of the second neutrino experiment is that they saw 23 muon events and no electron events. So they concluded that the second neutrino hypothesis indeed is correct, and there is one neutrino which is hypothesized by Pauli, which couples to electrons in beta decay, and there is a completely separate neutrino called muon neutrino, which is what occurs when a pion decays into a muon plus a neutrino. And within muon decay itself, there is both a muon and an electron, so there is both an electron neutrino and muon neutrino. But as I said, Yeah, as I said here, in the case of mu minus decay, I have a nu and a nu e bar, whereas in the case of mu plus decay, I have a nu bar and a nu e. So this established that there is a second neutrino which couples exclusively to muons, and Pauli's neutrino couples exclusively to electrons. Before I go on to the third neutrino, let me mention one important point. Yeah, the Cohen-Reines experiment took place in 1956. Okay, it ran for about 4-5 years, but the final results came out in 56. And this Brookhaven second neutrino experiment, it took place in 1962. So it's about 60 years since then. In these 60 years, there have been lots and lots of neutrino experiments. Some of them use so-called natural sources, that is, neutrinos from the sun, neutrinos from atmosphere, neutrinos coming with cosmic rays, etc. But there have been a lot of experiments using neutrinos with man-made sources. Every single one of them is an advanced version of these two experiments, because there are essentially two types of man-made neutrino sources. One, nuclear reactors, where we get nu e bar, and every single experiment which used nuclear reactors as a source is an advanced version of Cohen-Reines experiment. Other possible man-made neutrinos are from accelerators, and whether you have nu mu or nu mu bar depends on my electromagnetic separator. If I focus pi pluses, I get mu plus and nu mu, whereas if I focus pi minus, I get mu minus and nu mu bar. So when you hear the phrase reactor neutrinos, you can be sure that the source is electron antineutrinos. When you hear the phrase accelerator neutrinos, depending on the context, it's either nu mu or nu mu bar. And every single accelerator experiment since 1962 is an advanced version of the second neutrino experiment.
Electron neutrino being proposed?
Yeah, there was, but it was proposed because we are jumping ahead. There was the mixing angle θ13. There was an upper limit of 10 degrees set on it in 97, and so people wondered, what if it is 1 degree? And a proposal called beta beam was made in 2002. A lot of work was done on beta beams, including a large number of people from India worked on it. But in 2012, θ13 is measured to be about 8.5 degrees. So there is no reason to build a beta beam experiment. But if there is a compelling physics reason why we need an electron neutrino beam, we have at least a rough idea as to how to build that. There is also, you probably have seen some headline I've seen in the last week or 10 days about, there's an experiment called MICE, muon something cooling experiment, which tries to collect muons and then accelerate them to high energies with the idea of eventually colliding them. But one can also have what are called neutrino factories using these muons. So you have a long straight section and you subject the muon to a sudden force, then it will decay and you get a beam. Again, depending on whether it is mu minus or mu plus, you get a beam of mu plus nu e bar or beam of mu bar plus mu e. That is another technique by which one can hope to get a beam of electron nu e or nu e bar. So all these are quite expensive, and based on present problems that neutrino physics community is trying to address, we don't need them. So at the moment, all those proposals, they are there, they are on the back burner. Using the standard techniques, we can address the more pressing concerns. So that's how the field is moving at the moment. That's point number one. And let me mention another point, which is again nothing directly to do with neutrinos, but it will sort of address the question that you raised. If a pi plus can decay into mu plus and mu, in principle, it can decay into E plus and mu E also. And the phase space here is much more than the phase space here. So, naively, I would say decay of pi plus to E plus should be larger than the decay of pi plus to mu plus. But when you measure the rates, you find that this is 10,000 times smaller than this. So, a blind application of Fermi's golden rule does not allow us to explain this. So, which means that there is something more going on, and that is related to eventually what is called V minus A theory. I mentioned about this in a previous lecture. Sudarshan and Marshak and independently Feynman and Gell-Mann proposed the V minus A theory of weak interactions, and so this is an important prediction of V minus A theory, that if you have a spin zero meson decaying into two spin half particles, the decay will happen preferably into heavier mass particles than into lighter mass particles, because the amplitude is proportional to the lepton mass. So the rates are proportional to me square by mu square multiplied by the corresponding phase space terms, and me square by mu square dominates over the phase space. So that is why this decay rate is much smaller. Now let us briefly talk about the third neutrino. Before that, we should talk about the third lepton, which is called tau lepton. So this was discovered at SLAC in 1976, where they had a E plus E minus collider with the equal and opposite momenta and the same energy. And so, because of these collisions, you can produce lot of heavy particles. And one possibility, of course, is you produce mu minus mu plus, which will be back to back. But what these people saw is they saw events like this. They saw E plus E minus collision producing an E minus mu plus, and also there is a terrible energy momentum imbalance, and they saw lots of such events. They saw E plus E minus events with energy momentum imbalance. They saw mu plus mu minus events with energy momentum imbalance. And in addition, they saw E minus mu plus and E plus mu minus events also with energy momentum imbalance. So once again, it looks as if all the sacred conservation laws are being violated, which of course shouldn't be allowed. So in order to rescue the conservation laws, it was proposed that E plus E minus are actually going into a particle-antiparticle pair, which are completely new. And the mass of tau is about 1.7 GeV. So it's about 20 times more massive than mu1. And tau minus decay into E minus plus nothing. Also, it decays into mu minus plus nothing. And similarly for tau plus. So once again, what is this nothing? One particle, two particles, many particles. By looking at the spectrum of the electron and muon, we conclude that this nothing is actually two particles. So we write this as E minus plus mu E bar. This takes care of the LE conservation, and we conjecture that there is a new neutrino called nu tau, which couples only to tau minus. So we define L tau, which is +1 for tau minus and nu tau, -1 for tau plus and nu tau bar, and 0 for and based on which we can explain all the tau decays that are observed in the lab. And remember, why was second neutrino proposed? Because mu to E gamma was not observed. So similarly, the fact that same argument applies here, so which means that no L tau violating decays. That is, no tau to E gamma or mu gamma. And similarly, no tau to T minus L plus L minus, where this can be E plus E minus or mu plus mu minus. And similarly, no mu minus. So none of these decays, people have been searching for them for the past 40 odd years, and nobody has seen any such decay. So, but once again, nu tau is only a proposal. Is it really there or not? So there were two proofs for the existence of nu tau, one indirect and one direct. Indirect one came from left in 1990 or so. So here you have E plus E minus colliding. So in electroweak theory, it is proposed that there is a neutral exchange particle called Z0, and so this accelerator was constructed so that energy of electron and positron, their momenta are opposite and energy is equal to mz by 2. So you just produce Z0 at rest, and they have collected data for almost, LEP ran for almost 15 years, and in the 15 years they collected data with about 10 million Zs. But one of the first things they did is they did a scan. That is, they varied the energy of the beam. They didn't set the energy to be mz by 2. They varied the energy from mz by 2 minus 5 GeV to mz by 2 plus GeV plus 5 GeV. So that the root S which is T, the sum of two energies here. It varied from around 80 GeV to about 100 GeV. MZ is about 90. And then they looked at the cross section of E plus E minus collisions. So I hope you have seen what is called Breit-Wigner resonance in study of nuclear physics or atomic physics somewhere. So they get a curve like that. Actually, it's not quite like that, because the cross section keeps falling off as 1 over S. So it actually looks like this. Anyway, you mod out the 1 over S behavior and then you get the Breit-Wigner form. And you fit it to the Breit-Wigner formula and you get the width. So this span in energy at half maximum. So from which you calculate gamma Z. And you have the detectors detecting all the charged particles which are going through. So I can directly measure, for example, gamma Z0 going to E plus E minus, I can directly measure. Similarly, into mu plus mu minus, tau plus tau minus, all these into various quarks, all these I directly measure. So, having made that measurement, I define gamma invisible is equal to gamma Z0, or what we call gamma total minus gamma visible. So gamma total I get through the scan, whereas gamma visible I sit on the Z0 resonance and see how many electrons I get, how many muons I get, in general how many charged particles I get. Now first we find this is not equal to 0, which means that Z0 is decaying into particles which are not interacting with the detector. And then next thing we do, next thing the experimenters did is to calculate this. I can calculate theoretically based on Electroweak theory, and you find that this number is close to 3. In fact, you get 2.98 plus minus 0.04, something like that. So this tells us that there are 3 very light active neutrinos. What do I mean by active? It means they have weak interactions as prescribed by Electroweak model. That is what I call an active neutrino. So there are precisely 3 light active neutrinos, which is what we learned by studying beta decay, muon decay, pion decay, and the 76 lakh experiment, etc., etc. and the next step happened some 15 years later, which to some extent is a fancier version of this Brookhaven second neutrino experiment. You can call it Fermilab third neutrino experiment, though it is actually called donut. But life here is much more difficult. First, the neutrino has to interact in the detector and produce a tau. Tau has a mass 1.7 GeV, so correspondingly my neutrino energy has to be much larger. That is point number one. Point number two. As I said, nature was very kind to us here by designing a particle pi plus which decays only into muon and muon neutrino, but there is no such particle with such exclusive decay. But still there is something called ds plus, which is a bound state of charm and strange anti-quarks. This can decay into a tau plus and mu tau, and then you have to design a focusing apparatus which will pick up only ds plus and reject all others. So this is a fairly messy job, but the experimenters did that. And even more difficult thing is, so fine, I have a nu tau, comes and interacts, produces a tau minus. Identifying this tau. This is identifying a tau in a neutrino experiment is one of the most difficult things a particle experimentalist would attempt. And as far as I know, only 2 experiments attempted it. One is this donut experiment and another is an experiment called Opera. Both of them used the same technique. It's called observing a kink. So the idea there is the following. Actually, the neutrino interaction doesn't occur quite like this. It's more like mu tau interacts with the nucleus, produces a tau and a shower of charged particles. That is this is a very high energy neutrino with energy of some 20 GeV or so. And when such a neutrino hits a nucleus, the nucleus breaks up. So the idea is, the detector is made in the form of thin slices like this. So let's say a nu tau comes, interacts here, produces a tau, and if the tau goes like this, then by momentum conservation, this x should go like this. So I see a shower of particles starting from one vertex. And this tau is a very short-lived particle. It lives less than a picosecond. So you multiply picosecond by speed of light and you get something like a micron. So it travels a distance of a few microns and it decays. And it goes and decays, and the direction of tau is like that. And this is a fairly high energy tau. It has a energy of about 10 GeV or so, 10 to 12 GeV. And tau has many decays, and a prominent decay is a 3 pion decay. This is one of the prominent decay modes of tau. So you see a shower of particles in one direction and a shower of particles in another direction with sort of imbalance between the transverse momentum. That was the signature the experimenters used, and after a lot of struggle, I think they took data for some 6 or 7 years before they could get a conclusive signature that yes, we have seen tau production in our detector and attribute the production of tau to a neutrino coming from the accelerator and interacting in the detector. So this established that yes, there is indeed a third neutrino and it interacts with matter and produces a tau minus. So this is the picture we have, that there are 3 active neutrinos. Again, by active I'm using a very specific definition. When I call something an active neutrino, it has weak interactions as prescribed by electroweak model. 3 active neutrinos. One couples exclusively to electron neutrinos. Second one couples one electron neutrino couples exclusively to electrons. Muon neutrino couples exclusively to muons, and tau neutrino couples exclusively to tau leptons. And if you ask about the masses, one thing of course we can do, just as it is done in the case of electron neutrino, the way to determine the neutrino mass without any assumption is by kinematical means. So purely from kinematical means, we have the following limits. This is very recent, only about a month and a half old, from the Catherine experiment. Previous limit was 2.2 electron volts from Mainz experiment, and I do not remember the exact number, but something like this 100 could be 70. The exact number I don't remember, but of the order of 100 keV. And in the case of tau, it's about 30 MeV. But again, let me emphasize, these are limits coming purely from kinematics. We are not assuming anything else. We are not assuming oscillations, nothing. So this is the story so far about existence, why we believe these neutrinos exist, and second, how we directly detect them. Next thing is we'll talk about neutrino oscillations. I will give some brief introduction as to why people believed neutrino oscillations occur, and then we will discuss the formal theory of neutrino oscillations, first in vacuum and then in matter. And I will give you the first assignment sheet on coming Saturday, and you have to submit it the Saturday 1 week later. Okay.
Why is it like this?
No, that's the natural way to think. But these numbers are coming purely because of the Q value of the reactions in which the neutrinos are occurring. Electron neutrino comes in beta decay, and I have beta decays where the Q values are very, very small. So that is why I am able to get such a strong bond. Muon neutrino occurs, okay, both in muon decay as well as in pion decay, but I believe this limit is coming from pion decay, where the Q value is m pi minus m mu. That's about 30 MeV, 35 MeV. And this is like, let's call it 35 keV. So it's at 0.1% level. We are not able to measure the energies of pion and muon to better accuracy. And in the case of tau, it's one magnitude of larger, so it's one magnitude larger here. So this is pure kinematics, nothing more. Yeah.
Sir, what is the reason or logic that we are saying that tau neutrino and muon neutrino belongs to a neutron family? Means this may be something else. Means those particles exist, but this may be something else.
Yeah.
Not neutrino.
No, they are neutrinos. They are neutral spin half particles, so they are neutrinos. But they are not the neutrinos which are occurring in beta decay. Most definitely they are neutrinos.
So this neutrino means spin half neutral particles.
Yeah. So that's the nomenclature. Spin half neutral particle. Spin half neutral particle without strong interactions. Because otherwise neutron is spin half neutral particle. So if you want to get technical, the present definition of neutrino is spin half neutral particle without strong interactions. We call all such particles neutrinos. And if they have weak interactions as prescribed by Electroweak theory, we call them active neutrinos. Otherwise, we call them sterile neutrinos. And in sterile neutrinos, we talk about light sterile, intermediate mass sterile, heavy sterile, super heavy sterile, depending on the. These are all theoretical constructs. Sterile neutrinos, as of now, are theoretical constructs. They can have any mass. Depending on, when you have a data and a theory, there will always be some discrepancy somewhere. Sometimes you say, oh, the discrepancy is not serious enough, I will not bother. But some people who have a favorite model, they say, no, I have this very beautiful model and it can explain the discrepancy if this sterile neutrino has mass 100 keV. So people make a lot of arguments. So you have to sort of judge the value of that argument essentially by the data, by its ability of that argument to explain the data. So people talk about, milli electron volt, micro electron volt sterile neutrinos, electron volt sterile neutrinos, keV sterile neutrinos, MeV 10 power 10 GeV. Once you sort of let your imagination free, you can have anything you want.
So what about excited states of neutrino?
Well, see, actually, let me answer a question, similar question. People actually have been looking for excited states of electrons. Electron, as far as we know, is a fundamental particle with no substructure. But like we have proton, and then we have the quote excited proton, which is the delta plus resonance. So people have asked the question, can we have some kind of excited electrons? And people have been, periodically you will see papers from experiments setting limits on such excited electrons. But excited electron is easier to consider because electron interacts with electromagnetic field, which is almost all observations we make are based on electromagnetic interactions. So if you want to consider an excited neutrino, it can only be through that Z0. Theoretically you can consider, but I mean, okay, if you want to make a prediction about how this excited neutrino looks and how it can be discovered, yes, it's worth discussing. Otherwise, I mean, what's the point?
How can the excited electron if it does not have a substrate?
Yeah, I mean, it is expected to have a substructure. You can think of excited electron as some kind of quasi-stable bound state of an electron and a photon.
So similarly, we can have a quasi-bound state of neutrino and
Z0. Yeah.
And the donut experiment, how do we know it's a tau?
I mean, that's what. First, see, nowadays particle physics experiments depend a lot on the Monte Carlo simulations. Let me say that. So, but you look for a signature, to make a comparison with Cohen-Reines. Cohen-Reines looked for two things. The signal flash from E plus E. So two photons with energy, each with energy greater than 0.5 MeV, greater than or equal to 0.5 MeV. And some few microseconds delay and a photon with 2.2 MeV. Now, various other things can conspire to give you this signal, which forms the background for you. But they did whatever simulation they could based on their understanding of the interactions and showed that given their exposure, it is more likely that such a signal comes from neutrino interaction than through background. Same concept here. You look for events like this with two jets with a kink like this.
Are we also following the right side of the kink?
I'm looking at this and I'm looking at this.
So we know that we have few pions.
Yeah.
We have a tracker, everything to the right side.
So I have two vertices which are displaced from each other and they are not collinear with the beam. So I have one vertex giving a set of hadrons, another vertex giving a set of hadrons. And if I draw a line joining those two, that is not collinear with the beam. So that's the first thing I look for. Having identified such events, and I ask the question, how many such events are produced by nu tau interacting in my detector, producing a tau and the tau decay? and how many such events are produced through background. And I take data long enough such that signal by square root of background is greater than 5. Then I say I established a 5 sigma signal. Same thing they did with Higgs discovery. They were looking for Higgs decaying into 2 photons. And the probability, and in LHC environment, having 2 high energy photons is huge. But the probability that the 2 high energy photons combine to have invariant mass at Higgs mass, that is low. So, I mean, if you see the original LHC results, so this m gamma gamma is the invariant mass of the 2 photons, and let's say this is the Higgs mass. So the curve looks like this, and there is a tiny bump here. But if you do the statistics, each experiment had a 4 sigma signal and 2 experiments combined had a 5 sigma signal, and so they announced the result in 2012. And since then, of course, they collected many more events, so now things are much clearer. But in 2012, if you, I'm sure the videos are available on the YouTube, and of course the papers from those presentations, they are published in physics letters, and if you look at the figures in those papers, they look like this. You see this tiny bump, and based on which they claimed they have seen the Higgs.